Hello everyone. So in this lecture basically we want to cover mesh analysis. So first of all let us understand what is a mesh. So it is written here is that a mesh is a loop that does not contain any other loops within it. So pretty self-explanatory. So in this circuit if we want to find out the number of loops, that should be 3, right? So this is one of the loops, this is another one, and the whole circuit here can be also considered as another loop. So we have 3 loops here, but not all of them can be considered as the mesh. As you know, mesh should not contain any other loops within it. So this one here is one mesh and another one is this one. So these two can be called as mesh, but we have in total 3 loops. So generally what we can say is that all meshes are loops, but not all loops are mesh. Okay. Then for this analysis, mesh analysis, what we have to do basically is that we have to calculate the mesh currents for each of the meshes. So what is mesh current? We need to understand that first, right? Previously, for all the analysis we have done, we have actually calculated the branch currents for each of the branches. Like let's say for this one, this IA current is the branch current for this branch with resistor R1. Same goes for this IB, IC. But mesh current is quite different from this branch current. Let us try to understand that, how that is different from branch current. So here you see in this circuit we have 2 different meshes, and we have used this kind of notation here to represent I1 mesh current for mesh 1, and for mesh 2 this is the current I2 going in the clockwise direction, right? Now basically what mesh current is denoting here is that if I could divide this circuit into 2 parts such that it looks something like this. So we have one portion of the circuit with only mesh 1 and this one with mesh 2, so that mesh 2 is not interfering with mesh 1. It is not contributing to the voltages or current for mesh 1, and same goes for mesh 2 also. So in that case, whatever current is flowing through this circuit, this mesh, can be called as the mesh current for mesh 1, and same goes for mesh 2. Now when you think about that, what is the relationship between branch current and mesh current? Basically when you combine these 2 circuits, you are going to get this circuit, and what will happen through this resistor R3 is that there will be 2 mesh currents flowing through this resistor. One of them is this I1 and another one is actually I2, and this is actually this current is going from top to bottom, something like this, and this I2 current is going from bottom to top. So we can actually say that the branch current IB, which is going through our resistor R3, can be written as something like this: I1 minus I2. Okay, so this is the summation of both mesh currents, which is constituting the total branch current for this circuit, for this resistor R3. So in this way branch currents are related to mesh current, but what we have to do for this analysis is we have to measure the mesh currents for each of the meshes we have, so that we can solve the circuit. So now let us try to understand what are the steps we have to follow to solve a circuit using mesh analysis. So the first step is to assign mesh currents for each of the meshes we have. Like you see, for this simple circuit we have 2 meshes, we already know, and for each of these meshes we have to assign currents, mesh currents, like we have done here. I1 which is going in the clockwise direction, I2 which is going in the clockwise direction. So we can also take anti-clockwise direction, something like this, for denoting the currents. That is also possible, but generally for convenience what we do, we just take clockwise direction for all the mesh currents. So in this way we have to first of all define the currents, all the mesh currents, and then also define the direction for each of them. That is step 1. Then for next step, step 2, what we have to do is we have to apply KVL for each of the meshes we have. Like we have two meshes here, and for each of the meshes we have to apply KVL, Kirchhoff's voltage law, so that we can get two equations, right? So generally what happens is that, you know, the number of unknowns basically defines how many equations we have to find. We already know that. So in this case we have two unknowns. If you just talk about the mesh currents, we don't need to know anything about the branch currents, because if I get the mesh currents, using those I can get the branch currents or even the voltage drop across each of the resistors. Everything can be known to us. So only thing which is unknown or unknown variables are actually I1 and I2, these two mesh currents, and for that we have to form two equations. So if I just apply to KVL in these two meshes, that will be possible, right? So after that, basically solve the resulting n simultaneous equations to get the mesh currents. Very simple, just like our previous case, nodal analysis. So now we can see that nodal analysis that we learned earlier and this mesh analysis are kind of comparable, because previously in nodal analysis what we did is basically we calculated the node voltages instead of element wise voltage drops, right? And here also we are doing something different. Instead of you know, branch currents, we are measuring the mesh currents. And in the previous case in nodal analysis we applied KCL for each of the nodes. Here for each of the meshes we are applying KVL. Okay, now let us look at a problem, very simple problem, and we'll see how we can solve this one using mesh analysis. So let us try that. So here as you can see we have two meshes, right? We have two meshes, and we have to first of all according to our step 1 we have to define the mesh currents for each of the meshes and also their direction. So we are just going to take the clockwise direction for each of the meshes. So something like this one, let us call this I1, and for this one let us draw another current which is I2. So now we have two unknowns or two unknown mesh currents I1 and I2. We have to find them out somehow using you know, KVL. So we have to apply Kirchhoff's voltage law for each of the meshes, and this is a bit tricky. We will see how to actually do that. So let us start from here. You know, for mesh 1, let us write here mesh 1. For mesh 1, let us try to calculate KVL starting from here and going in the clockwise direction, same as I1. So we are taking the same direction as I1, and first we are encountering this 15 volt voltage source. So let us write that minus 15 volt. Then we will go again in this direction. We are encountering this 5 ohm resistor, and we know as our current is in the same direction as our KVL direction, so obviously we are going to get positive value for this voltage drop across this resistor, right? So that should be 5 multiplied with the mesh current I1. Now we will go in this direction. Now this one is a bit tricky because, you know, we are not actually calculating with our branch current. We have to calculate using mesh currents. And if you look at this one, I1 current is going in the downward direction and I2 is going in the upward direction. And both of the currents are actually contributing to the voltage drop across this resistor 10 ohm. So how to actually represent that using our Kirchhoff's voltage law? To do that, as we are going in the downward direction because clockwise direction, and in the same direction we have this current I1 and I2 is in the opposite direction. So we can write something like this. First of all, the value of resistance, which is 10, and in bracket we will have I1 is positive and I2 should be negative because I2 is in the opposite direction of our direction, our KVL direction, right? So that is done. Finally we have this element here, so it should be just, you know, plus 10, and that should be equal to 0. This is our first equation. And for the second equation we are going to apply KVL to our mesh 2, right? So for mesh 2, again we are going to, let's say, start from here in the clockwise direction. So first we are getting this one, so minus 10 volt. Then here, now here this thing is again a bit tricky. Now when we are going in this direction, because of our KVL, I2 is in the same direction as our KVL direction, but I1 is in the opposite direction. So now here if we want to represent the voltage drop across our 10 ohm resistor, that should be something like this. So plus 10, in bracket I2 should be positive and I1 should be negative, right? And then we can again go there. This will be very easy because, you know, we have I2 current going in this direction, same as the KVL. So we can just directly write 6 I2. So one thing to note here is that, you know, previously for applying KVL, we deliberately written the directions of, you know, polarity of each of the voltage drop, like something like this. But here we cannot do that because we are not calculating the branch current. We are measuring the or calculating the mesh currents, and for some of the resistors there can be two currents contributing for the voltage drop, like we have this 10 ohm resistor. So in that case maybe we are going to get polarity for I1 something like this, but for I2 it should be something like this. So in this way we cannot represent. We have to first of all understand what mesh currents are doing, what is their direction. So that is what is done here, right? So finally we had this, we already calculated for 6 ohm. Finally we have to calculate for 4 ohm, which is, you know, same in the, we are going in the clockwise direction, I2 is in the clockwise direction, so it should be positive. We can just write 4 I2, right? Another thing to note here is that, you know, for the side portion here, like here and here, for 5 ohm, 6 ohm and 4 ohm, whatever mesh currents we are getting, I1 is actually the branch current also. But for this case, across 10 ohm resistor, the currents we are getting, the branch current should not be exactly equal to the mesh current, because both of the currents, I1 and I2, these two mesh currents are contributing to the total current through our 10 ohm resistors. So that is the problem here, right? Okay, so these are the two equations we had to find because we have two unknowns, right? We had two unknowns, I1 and I2, and these are the two equations. And if you look at the equations, you will see that there are two unknowns there. So two unknowns, two equations, you can obviously solve this problem very easy. I am not going any further here. Okay. Now let us look at another problem. It is a bit difficult than the previous one because we have a dependent source here. Now to solve this one, again, the step one, the first step is to define the currents, the mesh currents and their directions. Let us do that first. So for this one, let us, you know, take I1. Maybe this one is I2 in the clockwise direction, and this one I3, again same direction, clockwise direction. Now we have to apply KVL for each of the meshes, and we will get three equations for these three unknowns. So let us try to do that. So mesh 1. For mesh 1, we will start from here. We will go in the same direction as our, you know, I1 current. So in this direction, first we are encountering this 24 volt voltage supply, so minus 24. Then again we will go in this direction, in this direction. Now here, you see, now here through this resistor we have I1 current in the same direction as our KVL, but I2 current in the opposite direction of our KVL. So it should be something like this: 10 I1 minus I2. That is done, right? Then again here we are encountering another problem. So we have 12 ohm resistor. I1 current is flowing in the downward direction, I3 is going in the upward direction. So the result should be something like this here: the voltage drop 12 I1 minus I3, okay, should be equal to 0. So this is our equation number 1. Then for mesh 2 is this one, right? So here again you can start from anywhere and calculate the KVL. So in the clockwise direction, we'll start with this one, and here now I2 is in the same direction as our calculation, but I1 is in a different direction. So we have to write here 10 I2 minus I1, right? And then we will go in this direction again. So we have 24, but only current is I2 in the same direction as our KVL. So it should be plus 24 I2. So that is our equation number 2. And now for equation number 3, we will have to apply KVL in mesh number 3. So here if you look at this one, we will start from here in the clockwise direction like this, and we have 12 ohm resistor, and same as our direction we have I3 in the upward direction but I1 in the downward direction, right? So we can write something like this: 12 I3 minus I1, right? Then we will go again in this direction. We have 4 ohm resistor. Here also in the same direction as our direction we have I3, but in the opposite direction we have I2, right? So we can write 4, which is the resistor, then the current going in the same direction minus the current going in the opposite direction. So that is done. Now finally we have this voltage drop, 4 I naught. So as this is a dependent source, basically we have to represent this one, this I naught, in terms of I1, I2 or I3. Obviously that can be done, right? Here if you look at this current I naught, this I naught current is going in the downward direction, same as I1. In this branch through our resistor 10 ohm, basically I1 current is going in the downward direction, I2 is going in the upward direction. Both of these currents are contributing to our total current in this branch. So we can write something like this: the total branch current I naught should be equal to I1, which is in the same direction as I naught, minus I2. Okay, so that value can be replaced here to get the total equation. So we will have 3 equations here for 3 unknowns, I1 and I1, I2 and I3. We can solve that, right? So okay, so far all the circuits we have solved using mesh analysis had only voltage sources, nothing with current sources, because when we have current sources in mesh analysis it causes some kind of problem, and we have methods to solve them, just like we face similar kind of problems when we solved nodal analysis with voltage sources. So similar thing will be happening here also. So we have 2 different cases. First case is when we have a current source which exists only in one mesh. So like in this circuit here, you see we have a current source, but that exists only in this mesh, no other meshes. So actually because of this current source, the whole circuit becomes even easier, because as we have 5 ampere current is flowing in this direction and mesh current is I2 in the opposite direction, we directly can write something like this for mesh 2. I2 should be equal to minus 5, because this branch current and this mesh current are exactly similar but in opposite direction. That's why we can do these things. So case 1 basically simplifies our mesh analysis, because we don't have to create two equations for two unknowns. One of the unknowns are already known to us because of this situation. Now for case 2, the calculation becomes quite difficult because we have to form super mesh, exactly like your super node in the previous discussion in nodal analysis. So here this happens when a current source, a current source exists between two meshes. Like in this circuit here you see we have a current source. This is existing between these two meshes, mesh 1 and mesh 2. As a result, the problem is we cannot actually measure the voltage drop across this current source. We don't have any information for that. That's why we have to form a super mesh enclosing this current source and anything that is in series with that thing. Okay, so we have this 6 ampere current source which is common to these two meshes. So we are forming this super mesh, but we also have to include this resistor because this is in series with this 6 ampere current source, which is causing the problem here. So we will do something like this, and because of this super mesh, what we can do, we can simplify the circuit something like this. So this particular branch can be omitted, kind of can be omitted. I mean, excluding this portion, we can calculate the KVL for the whole circuit here. That can be done. So how that is done? You see, if I start from here, if I start from here and try to calculate the values, obviously this is minus 20 volt, then we are going in this direction. If you think about the previous circuit here, all the currents for this mesh was contributed by I1. So 6 ohm will only get currents from I1 mesh current. So as a result, obviously I1 current is flowing through 6 ohm, and we can represent this voltage drop across 6 ohm as 6 I1, right? And if I go in this direction again, here for 10 ohm resistor the current is I2, right? So that is why we have to write 10 I2, and similarly here if I go here it should be 4 I2, but we are completely omitting the portion we had with this super node, right? We are completely excluding this one. Now we can just equate this portion to 0. This is our one of the equations, right? But we know here we have two different meshes, two different unknowns I1 and I2. So we have to form two equations to solve them. So another equation will come from inside of the super mesh. Just like our previous discussion in nodal analysis, what we did for nodal analysis, after we formed a super node, we got one of the equations from outside the super node and another one was from inside the super node. So here we are going to get another equation from inside of this super mesh. So what we can do is, if you look at this branch current, which is exactly 6 ampere, right? And I1 and I2 currents are the currents that are contributing to this 6 ampere current, right? So this branch current is being produced by mesh current I1 and I2, and I2 is in the same direction as the 6 ampere current, branch current, and I1 is in the opposite direction. So we can write something like this: 6 ampere branch current should be equal to I2 minus I1. So this is our second equation. So we have two different equations with two unknowns. We can solve this one. So in this way, for case 2, when we have a current source that exists between two meshes, we have to solve this using a super mesh. Okay, and for super mesh, what we do, for forming super mesh, we basically exclude the current source and any elements that are connected in series with that. Like we have this resistor here, we had to exclude that, including this current source. So in this way we can solve this kind of problems by creating super mesh. Now, based on the discussions we have made, we can finally solve a problem for mesh analysis with current sources. So here we can see we have two different current sources. One of them is independent, another one is dependent. So we have to use super meshes to solve this problem. But first of all, the first step is to define the current and their directions, the mesh currents and their directions. So let us try to do that. So here, let us call this one I1, right? And this one as I2. This is I3 and this is I4. So that is done. Now because we have current sources in between two meshes, and here also these current sources in between these two meshes, we have to form super mesh. And for these two, we can just form one super mesh like this, right? That can be done. And also for these two meshes, we can form another super mesh looking like this. But you see, we have two different super meshes overlapping with each other. In this kind of cases, we have to actually combine the two super meshes to form a bigger super mesh. And that is done here like this, you see. So we have a bigger super mesh by combining the two super meshes we had earlier because of these two current sources. Now we can solve the problem. For that, we have to form some KVL equations. We have to form one of the KVL equations from these bigger networks we have here. Okay, because of this super mesh, we have to form a KVL equation in this loop. So let us try to do that. So let us start from here and go in the clockwise direction, and let us call that super mesh. Super mesh. So I am going in this direction, and here this 2 ohm resistor is actually getting I1 current, so we can write 2 I1. Then I am going again in this direction. So here this is this should be, you know, I3 current is flowing in this mesh, so we can write 4 I3. Then again we are going in this direction. Now here for this particular resistor 8 ohm, we have two different mesh currents, I3 and I4. I3 is in our direction and I4 is in the opposite direction. So we have to write something like this: 8 multiplied with I3 minus I4. So that is done. Now again we are going in this direction. We have no components here, no components here, now here we have another components, 6 ohm, and I2 current is flowing in the same direction as our direction, so 6 I2 can be written here. Then again we have reached our initial point, so that is done. We can equate this equation with 0. Our first equation is found out. Now what we can do, we can actually form another KVL equation in this loop, in this mesh. So start from here and going in this direction. 8 ohm resistor is experiencing this current and this current. I4 is in our direction, upward direction, and I3 is in the opposite direction, so it should be something like this: 8 I4 minus I3. Then we will again start going. Here we have 2 ohm and the current is I4 in the same direction, so 2 I4. Again here we have voltage source and positive sign is in top direction, so here we have the second equation. Now we have 4 meshes. There are 4 unknowns, I1, I2, I3 and I4. So we should be getting 4 equations to solve this particular circuit. We already have got 2 equations. We need another 2. For that, if you look inside our super mesh, you will see we have 2 different current sources and because of these two current sources inside of our super mesh we are going to get two equations. Let us look at this one. Like 5 ampere current is going in this direction, this is the branch current, and obviously these two mesh currents are contributing to get this branch current. So we can write something like this. So 5 ampere current should be equal to I2 minus I1, because I2 is in the same direction as 5 ampere and I1 is in the opposite direction. So that is our third equation, and fourth equation we will get from these dependent sources. So here also this 3 I naught current is being generated from I3 and I2. So 3 I naught should be equal to I2 minus I3, because I2 is in the same direction as 3 I naught. Now here I naught should be represented in terms of I1, I2, I3 and I4 somehow. So how to do that? We know I naught is this one. So what is the current flowing through in this direction? Obviously in this path, you know, we have only one mesh. As a result, whatever current is flowing as mesh current should be the branch current. So I4 current is going in this direction but in the opposite direction as I0. So we can write I0 is equal to minus I4. We can just replace this value here. That will be our fourth equation. So we have 4 equations to solve 4 unknowns. That is how it should be done. Okay. So in this way, when we have current sources in mesh analysis, we can solve them by forming super mesh. That's all for this lecture. Thank you.